Hello everyone!
Today, we're going to demonstrate the principles of calorimetry by measuring the final temperature reached when a known mass of warm water is mixed with a known mass of ice.
The heat lost by the warm water is equal to the heat gained by the ice, allowing us to calculate the final equilibrium temperature.
So, in this experiment, we'll utilize a simple calorimeter constructed from readily available materials.
We began our experiment by first determining the mass of water. To do this, we measured the mass of an empty beaker using an analytical balance. After balancing it, we recorded the weight of the beaker. Next, we filled the beaker with warm water and measured the total mass of the beaker and the water. And after this measuring the mass of the beaker with water, we recorded the values. The difference between these two measurements yielded the mass of the warm water, which was 74.5 grams. Next, we used the same beaker measurement as before, which was 42.5 grams. Then, we followed a similar procedure to determine the mass of the ice. After balancing the scale, we recorded the mass of the beaker filled with ice, which was 79 grams. We then calculated the difference between the two measurements, resulting in a mass of 36.5 grams for the ice. Subsequent to determining the mass of the warm water and ice, we proceeded to measure the initial temperature of the warm water using a thermometer, which was recorded as 38 degrees Celsius. Afterward, we waited a few seconds for the thermometer to return to room temperature. Next, we measured the initial temperature of the ice with a thermometer as well, which was recorded at 0 degrees Celsius. Next up is the calorimeter preparation. First, we place ice inside a small beaker, which is then positioned inside a styrofoam cup. Next, we carefully pour warm water into the beaker containing the ice. After this, we place a second styrofoam cup under the first one and the third styrofoam cup over the first one to create an improvised calorimeter. Finally, we seal the gap between the two cups with Scotch tape to minimize heat exchange with the surroundings. We also ensured that the setup was stable and isolated. After sealing it, we leave it for 3 minutes to allow the heat energy from the warm water transfer to the ice. After 3 minutes, we carefully cut a small hole on the top of the third styrofoam cup to allow the thermometer to be inserted. The temperature of the water-ice mixture was monitored for a period of 3 hours. Readings were taken at regular intervals every 15 minutes to observe the temperature change as the ice melted and thermal equilibrium was approached. The temperature of the mixture was observed to decrease gradually over time, from approximately 30 degrees Celsius initially to 27 degrees Celsius and then to 25 degrees Celsius. After 3 hours, the temperature stabilized at 24.3 degrees Celsius, indicating that thermal equilibrium had been reached. The ice had completely melted and the final temperature of the water was 24.3 degrees Celsius.
The experiment successfully demonstrated the principle of heat transfer between two substances at different temperatures. The final temperature of 24.3 degrees Celsius represents the thermal equilibrium point where the heat lost by the warm water was equal to the heat gained by the ice, including the latent heat of fusion.
Further analysis could involve calculating the specific heat capacity of water using the experimental data and comparing it to the accepted value. Sources of error in the experiment could include the heat loss to the surroundings, despite the use of the styrofoam calorimeter, and inaccuracies in temperature measurement. More precise equipment and a more sophisticated calorimeter design could improve the accuracy of the results.